Hello everyone and welcome to this fifth lectures on papers live session. So this is not live session anymore, this is recorded and it will be put directly on YouTube and other platform later. So today we will read the new papers published in the Proceedings of the workshop on practical implementations on system experience in logic programming, and it has been published in June 1993. So at this time Erlang was already a language and it was already used at Ericsson. And the papers in question is called Carpe Diem, some implementation aspect of Turbo Erlang. So Turbo Erlang was a faster implementation of the Jam virtual machine, and actually I think it's probably also the Jam. So anyway, we'll take a look. And it has been written and published by Bogumil Hausman from the Computer Science Laboratory, LMTL Telecommunication System Laboratory. So the place where Erlang was created. So let's start with the abstract. Erlang is a concurrent programming language designed for prototyping and implementing reliable real-time systems. Erlang is used in a number of experimental telephony applications, both within and outside Ericsson. Our sequential implementation of Erlang, where Erlang programs are compiled into the C language, the implementation is called Turbo Erlang, was described in 6. In this paper we treat some implementation aspects of the Turbo Erlang system which were not treated earlier. So I did a mistake. Turbo Erlang is compiled into C languages, and that's interesting right now because I know another language doing particularly the same is called Mercury, and Mercury Lang is transcoding, transpiling and compiling prologue-like language into C language. So let's just take a look on the first note. I just want to have an idea at this time where was which company were using Erlang. So we have implementing a function language badly. Okay, Turbo Erlang, an efficient implementation of concurrent programming language. I'm not sure if this one, I don't know if I have it, perhaps it will be the next paper I will read. And the first one is prototyping cordless using declarative programming. I don't have this one as well, so we'll check a look. We'll check that later. So, introduction. Erlang is a concurrent programming language designed for prototyping and implementing reliable real-time systems. Erlang was developed at the Computer Science Laboratory, LMTL Communication System Laboratories. Erlang provides support for programming concurrent application, a special syntax for referring to timeouts, and explicit error detection capabilities. Some basic elements of Erlang programming are presented in the following section. Erlang, in its design, inherits some ideas from concurrent logic programming language. It does not allow destructive assignment of variables and use pattern matching for variable binding and function selection. In our recent paper, we have presented an efficient and portable sequential implementation of Erlang called Turbo Erlang, where Erlang programs are compiled into the C language. Portable means that the implementation can be ported to any processor having a GCC compiler. We have chosen GCC to allow global register allocation and usage of labels at first-class object, which in turn simplified return address administration and generation of unique labels. The Turbo Erlang system performs very well in comparison with other high-level language implementation like Sixtus Prolog, GC, and the Jam Erlang implementation, Erlang compiling to instruction for OK. Comparing further to Genus, in our system, each Erlang module is compiled into a C function residing in a separate file, and the module function can be accessed from other module with no overhead. In the Genus system, all programs are compiled into one C procedure, which does not allow for large-scale application. The comparison with C shows that the performance of Turbo Erlang is not far from the performance of highly optimized C code. We expect that after applying some compile time optimization, we will be able to run large applications in Erlang as quickly as the same application written from beginning in C or C++. For further details on the performance evaluation and comparison with other high-level language implementation, see 6. In this paper, we describe some implementation aspects of Erlang which were not treated in 6, for example, error recovery, catch and throw, and compiling Erlang control structure. To make the paper self-contained, we repeat some parts already described in 6. The paper is organized as follows. Erlang is introduced in section 2. In section 3 we present the Turbo Erlang abstract matching called Diem, and section 4 describes generation of the C code. The final conclusions are presented in section 5. So I think this paper, this one here, we will read it later. The Erlang language data object, an Erlang term, is either constant, integer, float, atom, process identifier, compound term, or a variable. A compound term is either tuple or list. Tuples are used for storing a fixed number of data. T1, T2, Tn is a tuple of size n. A list is either an empty list or a pair HL. Erlang does not allow destructive assignment of variables. On the first occurrence of a variable is its binding instance. Erlang programs are composed of functions. Definition of a function consists of a group of clauses, each having a head, an optional guard, and a body. The Erlang evaluation mechanism is based on pattern matching directed invocation. After a call of a function, the call is matched sequentially against each of the clauses defining the function in their textual order. After a successful match, the clause guard is defined. A guard consists of a simple test or a sequence of simple tests. It is evaluated, and if the evaluation succeeds, the clause body is chosen for execution. If no rule matches the call, an error is generated. Expressions in the selected clause body are evaluated sequentially. Modules. The module system in Erlang is based on function modularity. It works by limiting visibility of the function contained within a given module. Functions which are to be evaluated from outside the module must be explicitly exported. A function can be called from other module using a name qualified by a module name containing the function. Okay. Case expression. The case expression allows choices between alternatives within the body of a clause. So yeah, that's classical case expression. First, the expression is evaluated, and then the result is sequentially matched against pattern 1, blah blah blah. So I think all this part we can switch and move. So I think this part we can also just throw away from for the moment, or maybe I will read at least the first lines. Support for multi-process programming in Erlang consists of the following primitive: spawns for starting concurrent process and for sending a message to a process, and receive for receiving a message from a process. The primitive spawn module funct arguments start a concurrent process which evaluates the function module function argument, etc. Error recovery. Since telephone application programming requires error recovery in the event of an unplanned fire, Erlang provides explicit error detection capabilities. Erlang processes can be linked. Links are bidirectional to other communicating or cooperating processes. Upon abnormal termination, a runtime error, a process sends a special exit signal to all the currently linked processes. A default action is that upon receiving an exit signal, a process terminates and propagates the exit signal to other linked process. Another possibility is that a process can receive exit signals within a receive statement and perform any required action before termination. Okay. Where the message blah blah blah, catch and throw. The Erlang catch and throw mechanism can be used for a non-local return form function and for protecting bad code. To illustrate its usage, let us analyze the execution of the following Erlang function. So I think this one will work today. So in 1993, we already had working Erlang code that we can run today and execute and use today as well. So I think if you already do some Erlang, you already know all of those pieces of code. Code management. Erlang supports dynamic loading of code. Dynamic means that the code is loaded and linked at runtime on the use of multiple versions, currently 2, of the same module. Loading a new module version means that all new calls to the module are done to the new version, while all processes already executing the old version continue to do so. It is possible to remove the old version when there are no processes executing it. Erlang provides primitive for checking if there are any processes executing a given version of code. The above features, dynamic loading multiple versions of code, are required in telephony applications used to control telephony hardware, which cannot be stopped for software updates. Okay. So now the really interesting part. The Turbo Erlang abstract machine called Diem. The construction of the Turbo Erlang abstract machine, or Diem, have been influenced by ideas behind the conventional WAM on the Janus virtual machine, Janus compiled to C. Differences come from the fact that Erlang has a functional nature and has fully grown terms and has explicit notion of concurrency and time. Data object. An Erlang term is represented by a 32 bits unsigned word containing a value and a tag. The tag, 4 bits, resides in the least significant bits and distinguishes the type of the term. The value part of an atom is an index into a global atom table where the atom is represented. The value part of an integer is the integer itself. The value part of a list is a pointer to 2 consecutive heap locations with 2 tagged objects: the head and the tail of the list. The value part of a tuple is a pointer to a heap object containing tuple size followed by the tuple elements. The value part of a float is a pointer to a heap object containing a 2-word float value. The value part of a process identifier is a process identifier itself. So we have here description of what an atom is. So this is an index into global atom table, and at this time it was represented by I don't know by what was atoms represented. So integer cell. Okay, sorry. Okay, contain value on the tag. Yeah. The value part of a list. It's a pointer to two. Okay, so this is the description of the different term. I think we already have something similar right now and today. Data areas. So data areas are the code area containing loaded compiled C code on a stack on heap. The stack contains all frames with local variables and return addresses. The heap contains terms created by the erlang execution. The stack and the heap are located as one memory area and grow towards each other. Having the heap and the stack allocated together makes testing more memory overflow very efficient as we compare two pointers. Top of heap pointers and top of stack pointers. Resting in hardware register. Okay, that's a classical memory like managing system. So we have the heap, we have the stack. Each code frame on the stack start with return address followed by the local variable, which are accessed by integers offset from the pointers to the top of the stack. Frames are allocated only after a close guard is evaluated on if the closed body contains local variables and functions code. Okay. Frames are allocated and discarded by the macro allocate n and deallocate n with explicitly given frame size n. As we are using GCC, a return address is the stored address to a label in explicitly given frame size n. As we are using return address is the stored address to label in the generated C code on return from an erlang function is simply a go-to instruction to the given label. For garbage collection purposes, the stack structure can be obtained by looking for stored return addresses represented as unsigned integers and thus having the two last bits set to 0. To distinguish the return addresses from other data objects, the data objects do not use tags having the two last bits set to 0. Our garbage collection algorithm is a simple stop and copy one. After each garbage collection, the total size of the heap and stack area is dynamically adjusted to follow the execution requirement. It grows or shrinks. Okay. Registers. The team uses a set of registers declared as C global variables. Some of the variables are declared as global register variables. This feature is provided by GCC in contrast to CC. We have the following registers: top of heap pointers, top of stack pointers, return address pointers, pointer where to go when a function is ready executed, and argument register used to pass function parameters. Okay. Arithmetic. When arguments have mixed type or their type is unknown and could build time, we call a general purpose procedure to do the arithmetic. When arguments are integers, the basic arithmetic operations are directly compiled into C code. Type test and term comparison can reside in a quad or a body part of an erlang clause. The corresponding conditional instruction contains a label stating where to go when the condition is not met. The labels in query parts point to the next clause to be tried or to an error action if there are no clauses left. The labels in body parts point to an error action because a called erlang function should not fire. Term types are provided at compile time by word type test, like integer term. I think this is no is integer or is atom terms, since only terms with the required type can pass the quad at root time. Okay. So this part of the code probably changed. This is not no more integers and atom, it's is integer and is underscore atom function. To call an erlang function, we pass parameters in a WAM-like style loading arguments register and update the return address register. In order to destroy the argument register, all guard operation and tests are performed in temporary registers. On function returns, the return values is stored in x0. Okay, concurrency. Erlang processes are dynamically spawned and killed during the execution. Each process has its own heap and stack area. For concurrency purpose, the team provides suspension and scheduling mechanism. A suspending process stores its current state in its suspension record and is added to a scheduler queue. To guarantee a fair scheduling a process is suspended after a fixed number of reduction, and then the first process from the queue is resumed. I would need to reread this sentence in my head, but if I understand correctly, we have two scheduler or maybe dynamic scheduler queue. When one process is suspended, we put it directly in the scheduler queue, one another, and okay, fix a number of reduction, and then the first process from the queue is resumed. Okay, so that's just okay. We are suspending one process and we are fixing a number of reduction, so probably some ticks from the clock, and then the first process from the queue is resumed, so we are looping on those queue. To receive messages, each process has its own local message queue. Sending a message results in copying the message into the receiver heap and storing the message reference in the receiver message queue. While waiting for messages to be received, a process is swapped out and is added to the scheduler queue only when a new message is received. When the addition is done by a process sending the message or timeout occurs. Okay. Error recovery. Each Erlang process has its own local list containing all processes the process is linked to. As mentioned earlier, upon abnormal termination, like a runtime error, a process sends a special exit signal to all the currently linked processes. Sending the signal means that all the linked processes residing in the scheduling queue and waiting to be swapped in have their resumption addresses updated to execute the code responsible for exiting. A process, upon receiving an exit signal, propagates the signal to other still live linked processes. If the linked processes are to receive the exit signal within a receive statement, the signal is sent as an ordinary message. So that's the same procedure we have currently. So if we are catching those kind of signal, the message is can be available from the message queue. We can easily check that right now. Process flag, and we can set, for example, exit signal. That I don't remember if it's like that. We have the list here. Okay, every time. And I don't remember which one it's trap exit. Okay. True. It will be easier. Okay. And so now if I throw something like exit, I will flush my message. In theory, I should have something. Okay, I don't have it. Okay, is it working or not? Oh, naturally it doesn't. I always thought it was working. Weird. So it's crashing anyway. Okay, let's try it again. Okay, it doesn't work like that. If I spawn a process, I can do it easily, but it's weird. I was thinking it was working like that. Weird. So process flag trap exit true. We do something like throw. Oh no. Yeah, it's normal. I'm just stupid because I need to link to another process and it will crash and I will receive the message. Sorry about that. So spawn link fun exit, for example, and in theory I should have receive something just after. So I will just do that. And I got the exit normal signal. So the same behaviors. Behavior was present in 1993. Catch and throw. When a process executes a catch, the catch presumption address is saved in a local frame on the stack. Upon exiting or executing throw, the stack is checked for a saved resumption address, and the execution continues there. To know if a process executes within a catch, there is a process-specific counter of saved catch resumption address. An example of C code corresponding to a catch is shown later in section 4.5. Generation of C code. Using GCC and thus using labels as first-class objects allows us to structure the generated code in a very flexible way. In GCC, labels can be saved in global data structure, so the team execution can jump into different C procedures without calling the procedure themselves, and thus avoiding the C procedure call overhead. The only requirement is that the team uses only global or static declared data object during the execution. I would like to check for the GCC labels. I don't really know how this thing is working. Okay. Okay, interesting. So GCC allow to declare local labels in an nested block scope. A local label is just like another label, but you can only references it. with a goto statement or taking its address within the block in which it's declared. So I think this is a feature they were using at this time. Global data objects. The generated C code assessed a set of global variables, some of them residing in hardware registers corresponding to the team registers. There is a global atom table containing representation of atoms, global module table containing some Erlang module specific information, and a global function table containing addresses of exported Erlang function. The addresses at this stage are labels in the generated C code. Modules. Each Erlang module is compiled into a C function residing in a separate file. The C function consists of two parts, an initialization part and a code part. So when we are compiling those modules, every module is put in separate file. Okay, so the initialization part is responsible for updating the global atom table, exporting some local Erlang function, fetching addresses of function from other modules, updating the global module table. The initialization part ends with the C return instruction and is executed when the module is loaded. So that's interesting here, because we have the global atom table. That means we can lock the atom table and just block their creation if we want. I really need to read this part of Erlang code. The atom table management is an important feature. The code part consists of the C code corresponding to compiled Erlang function. The functions are accessed by goto instruction, where the required label is taken from the global function table. Calls or jumps to function in the same module are done directly. Labels to function in other modules are fetched from the global function table at load time. As the fetching is done at load time, all functions residing in other modules can be accessed with no overhead when the module code is executed. Function. To illustrate the C code corresponding to an Erlang function, let us analyze nrev/1. Okay, the corresponding C code are argument register. Why the 0 is local variable. The code consists of C macros. Labels written in italic out the macros C code is nrev1. Close test, allocate 1. That's okay. So this is the code directly used on the GCC part. Label acting as function address, and so this is the address of the function. Check memory overflow, create a list x1. Label, okay, go to error handler, indicate kind of fires. The above code uses some GNU extension to C language. They are locally declared labels, which simplifies the generation of unique labels. The locally declared label is used as well inside the call append/2 macro to generate the new return address. Where red is the address of label, red is one of the GNU extension to the C language. Red address is a return address register pointer. Okay, perhaps they will explain a little more this part just after. Case expression. If the case expression previously introduced in section 2.4 gets a 4, call case, case and blah blah blah, the corresponding C code is an argument register. The code consists of C macros parts written in italic as a macros C code. Test pattern. That's really cool hack they have used here. So they are generating directly. They are transcoding the Erlang code to something that could be interpreted by GCC, and in this case they are generating a full template that you can easily after compile in C using GCC. So that's really great. I would like to check the C code of Turbo Erlang. I will check after if we can find it on GitHub. Notice that the empty test pattern is expanded into go to red, since the return values n resides already in x0. The above C code illustrates an extensive use of locally declared labels to generate the required flow of control. Catch and throw. Another example of the generated C code is the following Erlang program containing a catch expression previously discussed in section 2.7. Protect bad code, catch through. The corresponding C code is okay, so we are allocating memory, we are checking if everything is fine, we are calling full, we say it's okay if it's okay, we deallocate and we return. The catch resumption address is stored in the stack called from on is charged up when a thrown is executed or an exit signal is received. Since it is possible to have many nested catch constructions, when a catch is executed, the corresponding catch resumption address is cleared. Each process has its own counter of pending catches. To know if there are catch resumption addresses to be found on the stack. Okay. Code management. A newly compiled Erlang module residing in a separate file can be dynamically loaded at runtime. First, the compiled C code is linked to the executing C code, and then the C procedure corresponding to the new module is called. Calling the procedure activates its initialization part, which in turn updates entries in the global function table corresponding to the module Erlang functions. If there is already an old loaded version of the module, loading the new version means that all new calls to the module are done to its new version, while all processes already executing the old code continues to do so. The old code is still loaded but cannot be accessed through the global function table. Okay, so the old process are still using the old code, and the new processes are using the new code, and it's because we have the global function table. So that means the global function table is being updated when an upgrade, and so when this table is updated, because it's global, the old module will have a kind of probably a copy of this global table, but the new one we have the new function table, and in this case with the new code. As mentioned earlier, it is possible to remove the old code when there are no processes executing it. We freeze the memory block containing the code. The information about address area a code occupies is saved in global module table at load time. to know if there are any processes executing the code, all processes have their stack checked for storage resumption addresses pointing into the code address area. Okay, so to remove the old code, we need to kill all processes. And after that, we can free up the memory and start to use the new code. No, we just kill the process and free up the memory, it will be okay. Conclusion. We have presented an efficient and portable sequential implementation of Erlang called Turbo Erlang, where Erlang programs are compiled into the C language. The presentation includes some implementation aspects not treated in our previous paper: error recovery, catch and throw, compiling Erlang control structure, checking for code removal. The proposed solution can be of interest to people who work on practical implementation of other high-level languages. The presented solution illustrates that the new extension to the C language, using labels as first-class objects, make it easy to generate a required flow of control and simplify structure and access to the final object code. Acknowledgements. We would like to thank Robert Victin and Mike Williams for discussion considering implementation aspect of Erlang. The C-level dynamic link editor was written at our laboratory by Tolbo and Tokvist. Sorry if it's not the good way to say it. We are also grateful to Hans Nilsson for his comment on earlier draft of this report. Okay, so let's check on GitHub if Turbo Erlang source code is available. I don't think so, but I would like to try. It's not on GitHub. I don't think we will have it. Yeah. Unfortunately, let's try on Google. So no, I don't think I will have access to this code. So there are other papers, so this one I think we will read it later. But in 1993 it was not so easy to find those kind of code. We can check on archive.org, but to be honest with you, I don't think we will find something. Didn't work. Great. Nothing. Okay. So I will not have any source code. I think we have more information here, but again, we have nothing like C source code or something like that. Okay, so I think it will be over for today. Just we'll check the references. New concept in parallel programming. Program telephony in Strand. So this one I need to check that, but I think I don't. It doesn't exist, or I can't find it. Programming telephony. I'm not sure I will find something. I will check that later. Concurrent programming in Erlang. So that's a book, so I will not read it. Efficient portable sequential implementation of Janus. Oh, this one could be interesting, in fact, and I don't think I have it in the list. So, efficient portable sequential implementation of Janus. Was in 1992. Okay. Okay. I think I will not have any access to this document. We'll check it later. Efficient implementation of concurrent programming language. I think we will read it later in another session. 60 Prolog users manual. Abstract Prolog instruction set. Implementation of architecture tutorial documentation. Logic programming conferences. It could be also great to have this one just to check it. Implementation architecture. I think I will use Scholar. It'll be easier. And I think I have nothing. Memory performance of this. Oh. implementation, of course. So I don't think I will have it as well, but there are other people talking about that, so perhaps later we will read it as well. So anyway, it's over for this 5th session. It was kind of interesting to have an idea of the first implementation of C implementation of Erlang using Turbo Erlang, and this page from the Erlang blog, the road to the JIT, was kind of interesting as well, because we have an idea of the different implementation created. So we have the prolog interpreter, Jam, Team. Now we are using the Beam. We have the Beam C, the hype. Actually, hype is a great piece of technology. I would really like to read some papers on it. The JIT, so Beam JIT, and I think we have this one, Beam assembly maybe. And so yeah, that's very great. So I think it's over for today. See you later, and yeah, have a good day, good weekend, good night, whatever you want. So bye.